In this video, we're going to discuss the work energy theorem. This is a really important concept for solving a lot of energy problems, so let's jump in. So the work energy theorem. So this is the main idea. The work equals the change in kinetic energy, or really the change in energy in some cases. So if we write out what the work equals, we know the work equals the force times the distance cosine of theta equals the 1/2 mass times the velocity squared, and since we're looking at the change in kinetic energy, it'll be the velocity final squared minus the velocity initial squared. So make sure you square these before you minus. You cannot put the square on the outside. And one other thing you might see when you're solving problems is you might see some graph that looks like where we can show this change using like a bar graph. So let's say there's some initial kinetic energy and then some work is applied. Well, this final kinetic energy would have to be this amount plus this amount. So the final kinetic energy would be higher if you add work. But if you were to subtract work, it would be less. So we'll see that when we do some examples. Alright, so let's do a first example here. So we have a box, or a bob pushes a box and then releases it, allowing it to slide on a surface with a coefficient of friction of 0.3 between the box and the surface. The box slides 5 meters before coming to rest. What is the initial speed of the box? Okay, so let's write what we have first. So the distance we know the distance travels 5 meters. We know the coefficient of friction is going to be kinetic because it's sliding, equals 0.3. And we're looking for the initial speed, v naught. So if we try to understand what's happening, a box is pushed with some force and then is released. So then it's released and it slides like this until it eventually comes to rest. So it travels some distance and then stops. So there is some v initial and then v final equals 0. Alright, and friction is doing a force in the opposite direction because it's slowing down this box. That's the force that's doing the work, that is slowing down the box. So if we fill in our chart over here, we know there's some initial kinetic energy because the box has some initial velocity, and we know the final kinetic energy is going to be 0 because the velocity final equals 0. So this will be at 0, and so the work that's done has to be the negative of that initial kinetic energy. So that's what our graph over here would look like. So let's start with our main equation. So we know that the work equals the change in kinetic energy. That's the big idea. So we can plug in what we know for work. So we're looking for the work due to friction because that's what's slowing the box down. That's what's causing that change in kinetic energy, times the distance, cosine of theta. And we know friction work is pretty much always going to be, well, it's always in the direction opposite to motion. So this is going to be go to -1 because theta is 180 degrees. And then we know our change in kinetic energy is the velocity final squared minus the velocity initial squared. But we know this velocity final squared goes to 0. So if we simplify this, we get the force of friction times the distance, and this is negative, equals, this should not be a negative actually. This should start as positive, but since this velocity initial is negative, we can bring the negative out. And we get this, so then the negatives cancel, and we'll get force due to friction times distance equals 1/2 mv naught squared. So now we need to solve for this initial velocity. So we don't know the mass, so we need to figure out how we're going to get rid of this mass. But we do know the distance, but we don't know the force due to friction. So let's draw our free body diagram, because I think that'll help us out. So we know that there's going to be some force due to gravity of the box, some force normal, and then the only other force acting on the box while it's sliding is this frictional force. So that's the only other force that's going to be applied here. And we know that the force of friction is equal to the force normal times the coefficient of friction. And because this force normal equals force gravity, because it's not accelerating in that direction, so we'll have the coefficient of friction times force due to gravity, and we know that the force due to gravity is just equal to mass times gravity. So if we plug that back into our equation over here, we get the coefficient of friction times mass times gravity times distance equals 1/2 mv0 squared. And now we get these masses that cancel. And so we have the coefficient of friction, gravity, distance equals 1/2 v0 squared. So now we can solve for v0 squared by saying 2 coefficient of friction gd, and then take the square root of both sides and get this as our final equation. And so now we have all these variables, so we can go ahead and plug these in. Okay, so if we plug these in, we get a velocity initial of 5.4 meters per second, and that'll be our final answer. So that's how we can relate the kinetic energy to the work to solve for some variable component. Okay, so let's do one more example. So we have a car accelerates from rest at 5 meters per second squared. How far has the car traveled when it reaches a speed of 8 meters per second squared? Okay, so we know the acceleration, first off, is 5 meters per second squared. And so it says it accelerates from rest, so that means we know the velocity initial is 0, and we want to find the distance at a speed of 8 meters per second. And so we want to know how far the car has traveled, so that'll be the distance. So that's what we're trying to find. So let's fill in our graph over here. So in this case, we know the velocity initial is 0, so there's going to be no kinetic energy to start. But then it reaches some kinetic energy when it has the velocity of 8 meters per second. So that means this work is going to be equal to the final kinetic energy. And so we can start with the original equation, saying work equals change in kinetic energy. But when we write it out, we'll have the force times distance cosine of theta equals the 1/2 m vf squared minus v0 squared. But this v0 goes to 0, so this component right here is just the final kinetic energy. So we could use this graph just to immediately go to work equals k final. So now we need to decide what is the force that's actually doing the work. So we're just looking at these initial and final positions. So we just know some force, some net force, is acting on this car to allow it to accelerate. So we can actually just put F net here, because we're looking at the net force in the x direction, because we know it's accelerating in the x direction, times the distance. And this cosine is just going to go to 1, because we know the force is in the same direction since it's accelerating, and the speed is increasing. So then we still have this part. Okay, so now what does F net equal? Well, we know by Newton's second law, the force net is just the mass of the system times the acceleration of the system. And so now these masses cancel, and we want to know this distance so we can divide by acceleration. And we can get this equation here. And now we have all these variables. We can just plug these in and get a distance of 6.4 meters. And so you might be thinking, this equation might look a little bit familiar, and that's because you can also solve this using normal kinematic equations, since there we have a constant acceleration. And so if you were to do this using kinematic equations, you could use this kinematic equation, where the velocity initial is still 0, and you get vf squared equals 2a, and then in this case the change in x is the distance. And so if you want to solve for distance, you would get the same equation as we had before by using kinematics. So this is how, that's the cool thing about physics though, is that as long as you're not breaking any principles, you can use different methods to get the same answer. But this won't always work because in this case we had this constant acceleration, and sometimes doing energy is going to be a lot easier than kinematics. Sometimes kinematics will be easier. So it's important to realize when you can use different techniques. But a lot of times it's going to be easier to use energy actually than kinematics. But in this case, it shows that you can use both. Alright, so that's all I got. Leave your questions down below, and thanks for watching.